Of course. So yeah, today TimeSeries InSAR. TimeSeries is really the next step up for what you did yesterday. Yesterday was single parent kilometry. TimeSeries is really the next step, and probably what most of you will be using if you're going to use this in your work, in your PhD, in your research. All right. There we go. So why do we do TimeSeries InSAR? If we have a lot of deformation, we really don't need it. So this it's ferrogram from the 2015 earthquake in Chile. And here we have meters of deformation. We have very good ground reflectors. So we get a very good coherence in the ferrogram. And in the single interferogram, you see all the signal. The signal is so large that the atmosphere doesn't really play a role. So you can get away with just making a single interferogram. A good correlation, and signal is dominated by deformation. We can unwrap it very easily. Like I said, meters of deformation. And this unwrapping, this integration of the phase signals is fairly trivial. However, in reality, interferograms are not always that good. In fact, often they are a lot worse than that. So you have two cases. In this case, a signal can be dominated by atmosphere, orbit, or DEM errors. So then the noise or the nuisance signals are bigger than your actual deformation signal that you're interested in. Or the correlation can be so high that the signal is very hard to detect by itself. This becomes especially a problem if your images are far apart in time, or if the perpendicular baseline, if satellites are far apart between the acquisitions. So TimeSeries InSAR is really a way of addressing all of these things. So it helps us in selecting our coherent pixels. So the pixels with a high signal to noise ratio. We can use the time dimension to estimate atmosphere and orbit errors by filtering, smarking, and spacing of time. We can estimate the DEM error because we have a whole series of images with a range of perpendicular baselines. And it helps us unwrap because we have the time dimension to help us with unwrapping as well. And then sub-pixel resolution is possible as well. So what this means is that if we have an image of, if we have an interferogram of that, at first glance, it might seem that every pixel in there is actually a point, but in reality, it's an area in space. Depending on the satellite, it's meters by tens of meters wide. So what we can do with TimeSeries as well is detect where within that area, where within that pixel, the actual scatterer is that we're measuring. So a few examples, improvement of coherence. So on the left here are the two images I just showed. On the right here is a point selection. So there's no filtering being done between here and here. All we're doing is removing noisy pixels. And you can see, especially for this one, it's quite apparent that a lot of the noise is reduced, and what we're left with is actually signal. And that's probably one of the most important reasons why we do TimeSeries InSAR, is to help with the correlation. It helps after unwrapping, we can separate deformation signals from orbit errors and atmosphere errors. So like I say, if you have meters of deformation, it's often not a problem, but here we're looking at about 10 centimeters of movement, slow slip in Mexico, over a very large area. So this is something like 200 or 300 kilometers. So we have our actual signal, and we can separate out the master atmosphere and the DEM error by using that time dimension. So, and with that, we reveal our actual deformation signal we're interested in. And then this is an example of the pixel sub-pixel resolution. So if we're measuring a point on the ground, we're only measuring range. If we have a lot of differences in height, the point is actually much closer than we think, because the height reduces the range in the line of sight direction. So what we can do with the time dimension is actually detect where the pixels are, and we can detect these buildings. So instead of all of these points being projected on the ground here, we actually detect that they're on the building and are moving up vertically. So a lot of ground to cover today. We have TimeSeries InSAR is basically split into two broad methods traditionally. We'll cover them both in some detail. I think what's important to take away from this is sort of the background assumptions and how these methods are working. So there are slightly different assumptions in there. We'll use one particular flavor of TimeSeries InSAR in the practical this afternoon. So even if you don't get all of the details of these methods, it's important to realize the assumptions that are behind these methods, so it will help you interpret your results. So broadly, we have two methods: persistent scatterer methods, small baseline methods. Persistent scatterer methods we'll start with. First, the small step back is to figure out what is actually causing decorrelation. So, like I said, our pixels on the ground are actually areas. They're not points, they're areas. And the radar signal we return is actually a sum of the radar reflection from all kinds of objects within that area. So if we assume you guys here are a pixel and the radar, I send the signal to you, I get a radar signal from that corner, I get a radar signal from there, and they sum up randomly, depending on where they are. And by that summation gives us one signal with a face value for that pixel. Now, because you're all sitting in a random position, one radar image doesn't tell us very much, the phase of it. It's only when we difference the phase from two consecutive images that we get an inferogram. So if I take an image now, I get a random phase, come back a week later to the exact same position, take another radar images. If all of you sit in the same place, I get exactly the same phase back. If nothing else happened, I can difference it, I can see nothing has happened. All of you move slightly back, I get a slightly bigger phase return from you. And the difference tells me how much you have moved. Now the problem starts occurring when I come back in a week, all of you guys have switched places, because then the summation I get from each and every one changes. And the phase return I get back is different because you guys have moved position with respect to each other. And that is what's causing decorrelation. Yeah, so you guys have moved, I come back, and I get a completely random phase back, and I difference it, and the difference I get is completely random. Sort of similar things happen if I come back to approximately the same position, but I get slightly further. So I take my radar image from here. Then the signal from you is getting slightly shorter, signal from you is getting slightly larger, so that changes the summation as well. Yeah, so that's the second cause of decorrelation. The first one is often correlated with time, because the larger the time span between two images, the more chance there are of you guys moving around, because you get restless, or coffee, or whatever. The second is a function of how much the satellite has moved between the two acquisitions. Yeah, the further I move, the bigger the summation changes. Yeah? If I move here, you get a lot closer, you get a lot further away, so the summation changes. Now, that whole story assumes that I get approximately the same strength of signal back from each and every one of you. But persistent scatterer assumes, or what persistent scatterer is looking for, is one scatterer that's much bigger than all of the rest. So whereas Jonathan in the back there, he's much larger than all of you, he's a big guy. So you get a very strong signal from here back. And then because summation is coherent, so we're taking the amplitude and the phase into account, what all of the rest of you guys are doing doesn't matter, because the signal I'm getting from Jonathan is so strong that if Jonathan doesn't move, the signal stays coherent. Yeah, in real life, this might not be a Jonathan, this might be a building, this might be a larger rock, this might be a rock face that's oriented quite well. Yeah, but we're looking for these strong scatterers, that stay consistent through time and that are very stable. And that's what persistent scatterers are looking for. How do we do that? First of all, we make interferogram with respect to one single, what we call a master image. So we have a whole series of images, 20, 30, 40 images, maybe more. And we select one master image, and then respect to that image, we make an interferogram with all of the other images. We don't do any filtering. If you do spectral filtering, you reduce your resolution, so your pixel gets bigger. Your pixel gets bigger, there's more chance of lots of small scatters being in. You want to keep your pixel as small as possible. You want to oversample because you want your strong scatter to be as close to the middle of your pixel as possible. You reduce your signal as much as possible by removing the topographic phase before you do a PS analysis. And then what you end up with is a single mask stack of interferograms. That's what you'll be making this afternoon. So if you have 20 images, you'll make 19 interferograms, one for every of your follower images. Looks something like this. So this is our master image here in the middle. And there's one line from that master going to every single image. And on this axis, there's time. On this axis, there's perpendicular baselines. Perpendicular baseline tells you how far the two satellites are apart from each other. And you want to pick a master image that's somewhere in the middle of both axes, because that gets you the highest coherence as possible. So it looks something like this. So master image is the 3rd of October 2014. So that's right at the beginning of the time series. And we get one interferogram for every follower image that we have. You can slowly see the signal building up here. And you can also see that the further in time we get, the lower the coherence seems to be getting. So how do we do this point selection in persistent scattering? Because in the end, that's what we're after. We're trying to select points with high signal to noise ratio. So if we go back to the standard equation of how interferometric phase for each pixel looks like. The interferometric phase is the rapid summation of the deformation phase, the phase due to atmosphere, orbit, topography, and the noise component. And what we want to estimate is how large this noise component is. We want to pick points with very low noise components. So we can either try to estimate the noise directly, which is going to be very hard, or we can try to remove all of the other contributions. And in fact, that's what we're going to try to do. Instead, so we're trying to estimate this noise component. So within the PS methods, there are again a slight subdivision. We have methods that use a temporal model, so they try to model the phase behavior of every pixel in time, and then estimate the noise from that. Or there are models who try to use a spatial correlation. So if you look at an interferogram, you see your phase, and interferograms with the highest coherence are the ones that show spatial correlation in the phase value. So we'll start with the temporal model. Example, the most well-known one, permanent scatter technique, developed in the early 2000s by Ferretti and all in Italy. Example of results over the San Francisco Bay Area, San Francisco, Golden Gate Bridge, somewhere here. I can see a nice, clean visible velocity image. So this is estimated from the time series and then estimate a linear rate through all the points. And you get something like that. So San Andreas fault is somewhere over here. And you can see movements along the faults. For the this type of PF method, for each pair of pixels in the interferogram, so we're looking at the difference between pixels within the interferogram. If pixels are close by, the atmosphere and the orbit almost cancel out. Yeah, if I have a pixel here, if I move slightly over here, I expect the atmospheric error and the orbit error to be almost the same. Yeah, so if you difference two close by pairs of pixels, the atmosphere and the orbit error cancel out. That's pretty much the assumption that this method works on. So if we look at pixel pairs, then we can say the interferometric phase difference between the two pairs is the combination of the difference in deformation, the difference in topographic phase, and the difference in noise. So if we can model these two pairs here, what we end up with is an estimation of the difference in noise between the two pixels. So the way we do this is For our entire interferogram, we try to select the best points within that interferogram, the points which we think will have the highest coherence. We select those based on a value called the amplitude dispersion. Now, this works on the assumption that we expect the points with the highest amplitude to be the best scatterers. Yeah, so buildings, rock faces, good scatterers that tend to have high amplitudes. So that's it's an assumption you make here in your pre-selection. For this method to work, most initially selected pixels must be PS, so you need to be fairly stringent in your selection. The amplitude dispersion is nothing else than the through time, the mean amplitude divided, sorry, the standard deviation of the amplitude divided by the mean amplitude. Yeah, so you want to have points that have a consistently high amplitude. So this is from their initial paper, and this shows the amplitude dispersion as a function of the phase noise. So you can see points with a low amplitude dispersion. So that means a low amplitude standard deviation and a high mean amplitude. That gives you a low amplitude dispersion. So these values, they tend to have low phase noise as well. So these are the points with the highest signal to noise ratio because you have low noise. Yeah, so these are good scatterers, these are bad scatterers. And you can see for low dispersion amplitudes, we get a very good correlation with phase noise. So we pick the points with the highest amplitude dispersion, and then we create a network between all those points. So for every point, we select the all of the nearest neighbors, and then we can do this phase differencing between the nearby points. So we can calculate, we can remove the atmosphere DEM error, taking these differences. And then we get, what we're left with is the difference in deformation, the difference in DEM error, and the difference in noise. Model these 2 points, these two terms. So the deformation, what the most important assumption that these methods make is that you have to estimate some sort of model for your deformation. So the original method assumes that you have linear deformation through time, so constant deformation rate through time. That's what you're seeing here. So you estimate a straight line through all of your points, taking into account that the points are rapid. So you get this sort of recurrent cycle of deformation. And then your phase noise is essentially the average distance of that line with all of your points. For your DEM error, we know that DEM error is related to your perpendicular baseline. So the further the satellites are apart, the bigger your DEM error is going to be. And that's given by this factor. So this term is constant, and it just depends on how far your satellites are apart. So this plot here, it's important to note the difference between this plot and the previous plot. So this is time versus phase. This is perpendicular baseline versus phase. So they're two separate, they're two independent estimations that we're doing. So this estimation estimates the phase as a function of perpendicular baseline. That gives you this entire constant here. And again, your phase noise is the difference between this line and each point. So for your network, you've estimated these parameters, these velocity and DEM errors. And then you can do some sort of outlier detection, make sure that all of your points within this network are actually persistent scatterers. You're still not entirely sure of that. And DEM error looks something like this. So for every point you get an estimate of how wrong your DEM is. And you get your mean line of sight velocity. And that depends on the model you're assuming. So in this case, they assume a linear model, constant velocity. You can do exponential, you can do a sinusoid, whatever you can estimate. Whatever you can estimate as a linear problem, you can put in there. Typically, it's a linear velocity. So that gives you the line of sight velocity. So then you have your network of very good points. You're fairly sure these are persistent scatterers. You have a deformation and an atmospheric delay of that. You can then interpolate that for the entire image. And then for for all of your other pixels that you have, you then remove the atmospheric delay, estimate your deformation model again. You do some filtering in space and time to separate unmodeled deformation from atmosphere. And you end up with something like this. A nice velocity plot plus a time series attached to that. So that was persistent scatter methods with time-based model in very, very short amount of time. Are there any questions about this?
Yes. Yes. In the network, you have a master in the center. The master machine in the center.
So there are two networks, no?
No. Network of interference.
Yeah, exactly.
Yeah.
So
it's quite easy to identify the center in time. So yeah. Firstly.
So you could have picked this one or this one, or even this one or this one as well. It's important to pick someone that's sort of in the middle. It's not critical. It doesn't matter. Shouldn't matter for the results if you pick this one or this one or this one or this one. There are guidelines in Ferretti's paper and in other papers on how to sort of estimate it, but it depends on the satellite, depends on the characteristics of the satellite, what is more important. For some satellites, the time might be critical. For some satellites, perpendicular baseline might be critical. That depends on the frequency of the radar, the bandwidth of the radar, these kinds of things.
Yeah, in general, can I base on the time of these? Okay, because after downloading the data, I have no perpendicular baseline.
You should. So like almost any, so things like gamma and ICE, they all allow you to estimate perpendicular baseline before you do any processing.
Okay, just calculate the baseline.
Just calculate the baseline with respect to between two images.
Okay.
So because if you just do it on time, you might end up picking this one, and then you might end up with a perpendicular baseline between this image and this image that are very close in time, or actually almost 1.5 kilometers apart. And for some satellites, that means it's completely correlated whatever you do.
Okay.
Yeah. So it depends on what. So for Sentinel, for example, the perpendicular baseline is within 100 meters either way. So the perpendicular baseline is never bigger than 100 meters or 150 meters. Like that. So this whole exercise becomes a lot less important if you can just pick one in the middle. If you're working with Cosmos SkyMap, for example, or Terrasur X, the baselines might be much bigger, and then this becomes much more important.
Yeah.
So, like I said, it really depends on the satellite.
Okay.
Yeah. Any other questions? All right. What slide to go to? Okay, so what this method is really good at, the temporal model persistent scatterer is detecting pixels in urban areas. It's not so good in areas without man-made structures. Why is that? And it all has to do with this amplitude selection and the way these emission networks made. So if you have all the pixels, so in an image, you do your initial selection based on the amplitude dispersion for this nice urban area, so you get nice amount of candidates. You reject your bad candidates, but you still have a nice network left. Yeah. Now what happens in rural areas, you don't have a lot of high amplitude targets. You might end up with only 3 candidates, so very few of them. Now remember, the atmosphere and the orbit errors, they based on the assumption that nearby pixels have the same atmospheric and orbital areas. If you have only very few pixels, this distance becomes very large. So then that assumption no longer holds. So you take your difference in atmospheric noise is so large, you end up with a lot of residual phase in there due to this atmospheric error. And then when you try to integrate it, nothing matches up, and you end up with no no candidate pixels left, and that's it. You basically you're done.
That also holds for area.
Not necessarily. It all depends on the quality of the scatterer. So you need consistently high amplitude scatterers. They need to be sort of evenly distributed over your image, or if they're not evenly distributed over your area of interest. I guess that's, you might have one corner of the image where you get no candidates, and that might be okay because you're not interested in that area. You need to have them evenly distributed over your area of interest. So you can then say, okay, we can lower the threshold and the dispersion amplitude a bit, get some more candidates, try and see what happens. But then what happens if you get a very dense network, but most of these points are no good. They might not be coherent. So then your face starts doing crazy things. You do your ejection again, and you end up with no points. So basically, if you have no consistently high scatterer pixels in your image, this method just breaks down. So an example over landslides here. You get some decent amount of points here and here, but nothing on the landslide itself. Landslides that tend to be forested areas, quite vegetated, and then you don't get any points on your area of interest. Another problem with this method is that it relies on your deformation model. So you use your assumption of linear velocity or exponential velocity, whatever you choose. But if your actual deformation does not follow this assumption closely enough, your phase residuals become too big again. You can't integrate your phase in your network and start rejecting the points you're interested in. So in this case, this landslide, it sort of goes, it's stable, and then it moves all of a sudden, and it's stable again, moves all of a sudden. Try to fit a straight line through there. The distance between your points and your straight line becomes too big. And it rejects that point because it doesn't appear to your model. So that's another big downside of this method, and probably one of the biggest downsides is that you have to assume a deformation model. That assumption needs to be valid for what you're interested in. So that's important to keep in mind. So the method is very robust, works very well in urban areas, but has some downsides, some big assumptions that might not be valid.
Does this mean you couldn't use TimeSeries analysis for co-seismic deformation?
So this particular one is not great for co-seismic. We'll go to the temporal one is much more suited for that. So that this describes what I just said. So you have some very good candidates, and these might be persistent scatterers, but you can't detect them because the phase is too the deformation doesn't adhere to your model. So you basically reject all of your points. So another example, Long Valley volcanic caldera. So this is caldera that expands and contracts, but then has interspersed with that has periods of quiescence, so where it's not doing anything, so it's quiet, and all a few months it's moving up or down, then it's quiet again for a while. So your linear deformation doesn't hold in this area. And area of interest. And then these are the results with your temporal model, which is scatter method. So you can see some points here, scattering here, some individual points here. But actually, most of the deformation we'll see actually happens in this area, and we're just not seeing. So we get about 300 high amplitude persistent scatterers in this area. That's not a lot if you start with hundreds of thousands of points. So the other flavor of PS methods is spatial correlation. And this is the method you'll be using this afternoon. And this works much more like how we detect high coherence. So when we look at an interferogram, the way we determine if an interferon is coherent or not is by looking at how well we can see the signal, how consistent the signal is in your image. So if there's a lot of spatial correlation in your image, there's high coherence. And this method works on that. So I'm trying to detect the spatial correlation. the reason this method was developed is sort of to combat, to work better in rural areas, so not be so constricted by high amplitude persistent scatters. And to also work better with where deformation rates are very irregular, so coseismic deformation, volcanic deformation, landslides, things that are just not very consistent over time, but where the pixels might still give you a good signal-to-noise ratio every time. So we start with the same starting point as the temporal model. You make a single master interference stacked interferograms. So in this case, the master is here in the middle, and all of the followers are, there's one interferogram for every follower image. So these ones go backwards. And you can see, again, this relation between time and coherence. So the images that are furthest away tend to be the lowest coherence images. And you can see the deformation building up, but it's not a linear rate. So you can see there's a big step between August and November here. Then again, between November and July, there are two big steps in the deformation. This is the volcanic edifice. Sorry, the volcanic source expanding rapidly at that time. So we have our stacked interferograms. Our favorite equation again. So we have our deformation, atmosphere, orbit, via noise. And again, we're interested in estimating for every pixel the magnitude of the noise. So in this case, we're not trying to model our deformation or orbit, our deformation and topography by using the time dimension. We're going to model it by realizing that the deformation, atmosphere, orbit, and part of the DEM error are correlated in space. Yeah, so deformation, stand here, I'll move to the next pixel, the deformation is going to be almost the same. We're looking at a coseismic interferogram, volcanic interferogram. Yeah, deformation is correlated in space. Atmosphere and orbit, we had already determined that they're correlated in space. And topography is partly correlated in space. So if we can estimate the phase component that's correlated in space, we can remove all of these contributors and left with just part of the topographic area and no noise, so we're almost there. How do we do that? We can do that by filtering our interferograms in space. You can filter your interferograms in space, so you do a bandpass filter, look for the low wavelength part of your signal. If you can estimate that reliably, you have your spatially coordinated space. So you can use different kinds of filters. So the ones that seems to be working best is a low pass filter plus an adaptive Goldstein filter. If you're interested in the paper, just assume, take it from me that this is one of the better methods of doing it. And that gives you spatially coordinated phase. So how does that look? So if your original interferogram looks like this, so you have some signals and you can see some spatially coordinated phase. But on top of that, there's this random noise, this speckly kind of noise. So that's what you want to get rid of. So you filter your interferogram, you get a nice clean looking image, and you take the difference between this, and you end up with your spatially uncorrelated phase. And then this is partly noise and partly this spatially uncorrelated part of the photographic error. Yeah. So this is your original interferogram phase. This here is everything in green, your spatially correlated phase, and then this is the combination of these two terms. So the spatially uncorrelated part of the topographic error is still correlated with perpendicular baselines. So that's the same thing we used in the temporal model, is that the topographic error is directly proportional to your perpendicular baseline. So we can estimate that bit by fitting a line through our phase values as a function of the baseline. So that's this plot again. So all of these points are these two terms together. And then the red line indicates the blue bit, so the topographic error. Yeah, and then the noise value for every image is the distance between your red line and the point. Yeah, so that gives you an estimate of the noise. So like I said, temporal coherence then estimated from the residuals. And then the way STAMS works is it iterates that because you can then filter by weighting based on your noise components. So that's iterated several times to get the most reliable estimate of your spatially coordinated phase. So same area we looked at before, Long Valley caldera. Where before we had 300 persistent scatters, now we have 29,000. This is just the location of the points. This doesn't actually tell us anything about the phase. We'll get to that later. So this shows you the phase of the selected points. So we saw our single master timestamps earlier, where especially the images far away in time were very noisy. It was hard to see them signaling. By just selecting the points, these images clean up very nicely. And we get an idea of the reliability of our point selection. Yeah, if these images look nice and clean, it means we're only selecting points with nice signal to noise ratio. Then we have to do phase unwrapping. So you did phase unwrapping yesterday, I believe, in the single mass timestamp. So we have to do this. So with the temporal model, so the other PS methods, phase is unwrapped by essentially fitting the phase values to your deformation model. So you assume this linear deformation, and then you estimate your phase unwrapping in time based on that. But that's a problem if we want to get away from assuming this deformation model. Yeah? If we estimate our model, our results are always going to follow this model, and that's something we ideally don't want. So we need another strategy. So we have 2D unwrapping like we did yesterday. So we have our selected pixels, and then you get these phase residuals, and you try to connect them somehow intelligently, preferably. And that's a 2D problem, so we have a limited amount of information. Now what we have in STAMPS is that we have a 3D problem. So we have residuals in space. So we have a 2D problem, we have 4. But we also have information in the time domain. So we have more information to estimate the same amount of models. So we can use the space domain to help us with that unwrapping. That gives us a much more reliable result compared to just the 2D problem like we did yesterday. So we can use the time domain to help us constrain this unwrapping issue. And you can see we get a signal through time. There is which is not very consistent in time, so it's not very linear in time. You get episodes of deformation. So nothing happens. Then between June and July 95, all of a sudden, you can see movement happen. Same here between November and July, November at 97 and 98, all of a sudden there seems to be a step in the deformation. So it's not very linear in time. We can use the time domain to estimate atmospheric and orbit errors as well by filtering in time and space. So with those errors removed, looks something like this. So again, this big step in between 97 and 98, it's not linear deformation. So this is a comparison of the two approaches we've looked at so far. This is the temporal model that assumes this linear deformation. You can see where there's extra deformation, not another signal left. If we use the STAMPS method, the spatial correlation approach, we cover the caldera quite nicely. We get a nice idea of where the signal is located. And this is the kind of result you can actually use to model where's the source located, put a nice movie model, try to fit it, calculate residuals, this kind of things. There's just not enough information in this model present. So validation with some ground truth is what we're measuring actually what's happening. So these green points here are leveling results. These red points are InSAR points. GPS, we don't have a whole lot of GPS, but they're on this one. And then we have EDM, electronic distance measurement, I think it stands for. It's basically two poles, and then you measure the distance with it, and you do that consistently over time. And you can see all of the results match up quite nicely. InSAR follows the EDM measurements very nice. So we have good agreement between the results. Another example of nonlinear deformation where the spatial correlation method works quite nicely is Eyjafjallajökull. So I lived in Iceland for 2 years. Pride myself on my pronunciation of that. So might have ruined some vacations in 2010, caused lots of flight delays, airport closures in the UK and Northwest Europe. You can see this is actually even more non-linear than the long valley deformation was, so nothing happening. And then between February and March 2010, all of a sudden you can see this inflation here. And that inflation stays in place, so nothing more happens until May, and you can see a deflation starting to happen right next to that. There are really two separate sources, both of them are very non-linear, and the spatial correlation method is able to select lots of points, cover the deformation very nicely. And we're dealing with about 20 centimeters of deformation. And we're extracting that quite nicely. One other nice thing about the spatial correlation method, so by not estimating a temporal model, we can say something about our errors in our velocities. We can say something about the probability density function. So how reliable is every point? That's essentially what we want to know when we're looking at these results. So these are our subsidence rates over Bangkok. Lots of problem with groundwater extraction. So a lot of deformation, 30 millimeters a year. But we see some areas where the results look a bit spotty there. So this looks very correlated, but this looks a bit, goes up and down. And are these results? Is this actually what's happening, or is this just noisy results we're seeing? But then, if you try to estimate your standard deviation of your velocities, you can see this area has a very low standard deviation, so it's very reliable. If you go to this area, the standard deviation gets much higher. So we have much more confidence in the results here than we have here. And that's as important, if not more important, to know than actually which results are reliable, which results can I trust, which results can't trust. And the reason we can estimate that is because we don't make any assumption on how the velocities behave during our point selection, because that would bias our uncertainty analysis. Right? So those are the two main PS methods. Spatial correlation method works more general case, so it works better in rural areas, doesn't make any assumption on the velocity model. But you need to have deformation that's spatially correlated. So if one point is moving and all the other points are not, probably nothing. Temporal model is more rigorous, so you can extract these individual points that are not spatially correlated, but it doesn't work very well in rural areas, and it doesn't work very well if the deformation doesn't follow the model you assume. Any questions on that? Whole lot of information.
Yeah.
Yeah. Let's go ahead. Okay.
Okay. I have one question. In case in the examples you have quite large velocity, at least centimeters, but in some case it has a very small velocities over a very long time. For example, 3 years, and it's up to just only 3 meters a year, for example. So how can you advise? Because I know that in case very small signal, so in that case the signal to noise is very, very small. So how to deal with the errors?
So there are multiple parts to your question. So first of all, so the smallest deformation we looked at are in the order of a centimeter a year.
Millimeters only.
No, what we've looked at here is about centimeter a year. It all depends on how many images you have and how they're spread through time. So if you have a very dense amount of images over 3 years, so let's say with Sentinel, we're now almost 4 years in. We have something like 100, over Europe at least, we have 160, 170 images. If you put that in the time series, you're going to get results of in the order of a few millimeters a year precision. If you look at older data, MVSat, for example, over the 8 years that MVSat was, no, 6 years that MVSat was acquiring data, you might only have 20 images. Then you're probably not going to get to a few millimeters a year precision. Then you might be stuck at between half centimeter and a centimeter a year. So it's all a function of how good your data is really. So if you have 150 images, you're going to get probably down to a millimeter a year. And then the time series methods will work for those small results, for those small, and you're going to get, if you would then estimate your standard deviations, you would get very small standard deviations. Does that answer your question?
Yeah, I have tried with, for example, TimeSeries data, and you have mentioned that it has very, very large propagating color baseline. And I think even we can correct some them error. It cannot be done perfectly, so it still exists. And in case TimeSeries, for example, we cannot still the longer temporal baseline. Yeah, just 2 or 3 repeats only. So I think for that case, it's quite hard.
Yeah, well, all of these methods require you to have. So InSAR is a opportunistic technique. So you're dependent on the quality of scattering you're going to get. So you need a certain amount of coherence coming from the ground. If you don't have coherence, you can't select coherent points. So there are areas in the world where even with the highest quality data, you might not get results because you're not getting a good enough reflection from the surface. Now then, it also depends on what kind of frequency you use. So Teraser X is X band. So it's the shortest wavelength we have. So that's the worst for vegetated areas because it's influenced most by leaves, vegetation. If you move to the other end of the spectrum towards L band, so ALOS-2 Japanese satellite, it interacts much less with vegetation because that has a wavelength of about 24 centimeters, so something like this. So then the wavelength becomes bigger than the leaves and these kind of things, and interacts much less with it. So the reflection then comes from the tree trunks, from the ground itself. They get much better quality. So in vegetated areas, higher wavelengths work better. So yeah, but I guess in terms of time series, the point to remember is that time series methods do not create coherence. They're just detecting which points are coherent. So if you don't have coherence, no matter what method you use, you're not going to get accurate results. The information just isn't there. Yeah.
Sorry, I didn't get an explanation for the spatial correlation. So the assumption is that your signal is spatially correlated.
Yeah.
And then, so what happens because the atmosphere is also spatially correlated?
Yes.
So you do the same thing with the example.
Yeah. So what's important to remember here is that what we're trying to do here is not to detect our deformation. What we're trying to do here is detect how much noise is fixed. Yeah. So we're not trying to find out which bit of this is deformation or which bit of this is we're trying to find how much noise each pixel has. Once we know how much noise each pixel has, we can estimate a coherence for that pixel. And then we can use that coherence to go back to our original image and just select the points with the good. Yeah. So then we're back to this essentially. but we then know that the points we've selected have a very low noise. And then we can use our filtering techniques to get rid of this. So this one is then still correlated with perpendicular baseline. And these two we can estimate by filtering in time space. And then what we're left with is separation. So it's important to remember that we're selecting and then we're going back to the original phase. Yeah? Other question?
In the case the information is not computerized.
So there's no assumption being made during the point selection. There's no assumption being made on the velocity. So the time series you end up with is the original time series. You can then unwrap. The only time you make an assumption is when you. So this has no assumption on your deformation model. Then your phase unwrapping, we still don't make an assumption on your deformation model. The only time stamps this particular implementation makes an assumption on the deformation model is when we estimate the velocity. Yeah, because to estimate the velocity, we just fit a straight line to our points. But this is just the least squares because we have our unwrapped points, so you're just trying to estimate a velocity through a set of points. So you already have a linear time series. So this is not like small baseline where you have to do the inversion. We'll get that bit later. Yeah. The only thing we're trying to estimate is instead of having this time series, which might be exponential or whatever, we want to estimate our velocity. Then we say, okay, we assume a linear velocity through here. But you can look at your time series by that point because you have it unwrapped. You can say, okay, I see a sinusoid in there, or I see an exponential, and you can estimate that. So what the assumption stamps does not make is in deformation model during the point selection. So your point selection does not depend on the kind of deformation you assume. That's we can talk about this after if you want.
Sorry, baseline term estimation.
Yeah, I'm gonna
running out of time, so maybe
like,
Karsten will come upstairs.
I have like at least 20 minutes left. So if you want to take a break, we can do that as well. I got 90 slides from that. So
Well, so let's hold the questions, please, if you don't mind, and maybe Karsten can come up with that at some point throughout the day, if you have or not.
yeah. So do you want me to continue for 20 minutes, or do you want to have a coffee break and
I
then?
think we don't have this space for the rest of the morning. We have it for about half an hour. So
Okay. Well, I should be able to manage that. Okay, so time series InSAR are two methods. We've covered PS methods. The other type of method, small baseline. So before we were looking for these persistent scatterers that were where we have these big dominant scatterers, and we get a consistent signal almost no matter what the baseline does. What the small baseline methods are doing is we want to use as many pixels as we can. So let's also use these distributed scatterers where we have lots of little individual scatterers. But let's minimize the baselines in our interferogram. So only make short combinations. So we want to make combinations where both the temporal baseline, so the separation in time, is very small, and where the spatial separation, so the distance between satellite acquisitions, is very small. And that minimizes the decorrelation as an effect of this thing. All right. So instead of this star-like network that we got before, where we had one central image and then an interferogram with all of these others, we make a network of interferograms where we only make short hops between images. So we're minimizing our spatial and temporal baselines. We use spectral filtering this time because we care less about resolution, we care more about quality of our signal, so we tend to filter it. We multi-look each interferogram, so you did that yesterday as well, to increase our signal-to-noise ratio. Multi-look is really a very simple, you can see it as a very simple filter, simple averaging of your phase. We then phase unwrap each interferogram just in 2D, same as you did yesterday, but for a whole stack of interferograms. And then we find pixels which are coherent in most of our interferograms. And then we need to invert in some way for displacements. Now, the first 3 bits of this is essentially conventional InSAR. It's exactly the same as what we did yesterday, except we do it for a whole stack of small baseline combinations. Yeah, so this bit is very simple. This bit is a bit more complicated. So invert in some way for the temporal displacement. Now, you do that in many ways. There are many flavors of this method. So you can use singular value decomposition, squares, constraint, least squares, L1 norm minimization. And really all these methods are just different ways of getting from your sort of small baseline network to a commutative displacement through time. Nice thing about small baseline approach is that you have redundancy in your network, so you can take multiple paths through your network to get through time, and this allows for checking of unwrapping errors. And this proves to be quite a useful property of small baseline. It's nice example to begin with, displacements of Etna. What they've done here is they've processed 2 images from different look directions and then decomposed them. So what you get is a vertical displacement, east-west displacement. Mount Etna, you can see there's east-west movements of the flank, and superimposed of that is vertical deformation. So there's some lava fields that are contracting and some landslides moving. So some variations to this, you can make it a bit more complicated by using a 3D phase unwrapping instead of 2D phase unwrapping. So you get a bit more accuracy with phase unwrapping. Example of around Tehran, so groundwater, lots of wells in the area, and causing significant subsidence. And instead of multi-looking your images, you can also try to do this on single-look images to increase your resolution and be a bit better at finding isolated stable pixels. So when resolution is important, use these single-look methods. So STAMPS has a small baseline method incorporated in that. It uses pretty much the same algorithm as the persistent scattering method. So trying to find the spatial correlated phase and removing that and then estimating your DEM error. And then finding for every point the noise is useful points. I won't go through that again. You select your points, then you unwrap using again 3D phase unwrapping, same as before. So using a time dimension to help constrain your 2D phase unwrapping. And then you need to invert your time series, your sort of small baseline time series into a commutative time series. And then when you do that, it looks something like this. So again, this is AF related. This is about 15 years earlier though, ERS data between 93 and 2000. And you can see some inflation period here in 93 and another inflation period in 99. Anyone know why this inflation is negative? This one's positive. Any guesses?
Relative to the reference date.
Yeah, so the reference date's in the middle here. So everything before inflation is negative, everything after inflation is positive. So what we often do is put the reference date at the start. So essentially subtract this value from all the other interferograms, and then you get a nice sort of linear time series. So if you compare small baseline with PS, you would expect to see the same signal, but not necessarily the same pixels selected. So you can see, if you look closely, small baseline selects more pixels. I'm sort of apparent in this area here, you can see the gaps are much smaller. So there's some overlap in the pixels selected because in essence you're looking for coherence, so you expect some overlap. So about 91,000 pixels are overlapping. And the PS pixel has some unique pixels, but small baseline selects much more pixels. But we expect it to be much more distributed scatterers than persistent scatterers in rural areas, just because of the nature of the area. This plot demonstrates the same thing again. So the pink pixels are the ones that are estimated both by small baseline and persistent scatterers. And these on the axis here are the coherences estimated. So this for persistent scattering, this for small baseline. See, for the pixels that are in common, we get a nice linear correlation between the two. And then we can see the small baseline blob is here, and the persistent scattering blob is down here. So these are the pixels that are uniquely selected by each one. And what this tells us is that there is some value in combining the two methods as well. I'll get back to that later. Small baseline example again over Turkey. So there's a North Anatolian fault right there. These are interferograms going further west along the North Anatolian fault. And what we're expecting to see is a movement along the fault. It becomes especially apparent in the ascending tracks because the geometry is a bit more favorable. We can see a movement of the north side with respect to the south. This is all done using small baseline methods in stamps. So, like I said, small baseline PS methods. There's a bit of overlap between stacked pixels, but there's also a lot of pixels that are uniquely selected by range methods. So the natural thing would be to come up with combined methods. So SatSense combined method. Another well-known method is InSAR. I won't get into that. But read the paper if you want. So the way SatSense does it, it essentially runs both the PS and the small baseline method on point selection. Then afterwards, the points are combined, and then you do a phase unwrapping of all points together. You weight the points with respect to the signal-to-noise ratio, not bias your results too much. And then you get results over AFF vehicle, again, much more coverage than before. And you see these deformation episodes, 95 and 99. So before I said it was a 93, actually it's a 95. And that's again due to where your reference image is. So this is of course not where the deformation happens. This is where the deformation happens because you go from this image to this. So this is where the difference happens. So the deformation happens somewhere between 93 and 95. And you see that much clearer in this result because the reference area is now clear at the start. So to summarize everything we've covered today, which is quite a lot, persistent scatterer relies on these very stable pixels which have a dominant scatterer. Small baseline methods is a bit less strict in the points at once. And it does that by looking for, by minimizing the temporal baselines, so maximizing coherence in your interferograms. Important to reduce your non-deformation signals, and all methods essentially do that by modeling and filtering in space and time. PS techniques, best for urban environments, but can work in rural environments. Small baseline is a more general approach. Combined approach is possible as well. That's all I have, which is quite enough for this morning, I think. So yeah, I'll be at coffee and I'll be at lunch as well. So I'm sure there are a ton of questions. Don't hesitate to approach me. Come have a chat to me. Right. Yeah.
No, it's for me.
It's too much ground.